Hello students, today in this session I will discuss about the derivation of expression for Maxwell-Ampere equation, or it is also called as Ampere's Maxwell equation. So after that I will discuss the derivation for an expression, this expression for the displacement current, and then the third topic I will discuss is about the derivation of expression for the wave equation using the Maxwell's equations in the free space. Now let us start with the Ampere's Maxwell's equation. Now the Ampere's law in differential form is given by del cross H is equal to J. I will call this as equation 1. Now let us assume JD is the displacement current density in continuous medium. So if we consider J subscript D to be the displacement current density in the continuous medium, therefore replace J by J plus JD in equation 1. So we will get del cross H is equal to J plus JD, we will call this as equation 2. Now in order to further derive this equation, we will apply divergence on both sides of equation 2. Apply divergence on both sides of equation 2, then it is del dot del cross H is equal to del dot J plus JD, we will call this as equation 3. According to the vector analysis, the divergence of curl of any vector becomes equal to 0, then hence we can write, since divergence of curl of a vector is 0, then we can write the equation 3 as 0 is equal to del dot J plus del dot JD, or del dot J is equal to minus del dot JD, we will call this as equation 4. We know that divergence of current density at any point in electric field is given by del dot E is equal to rho by epsilon naught. Rho is equal to del dot E into epsilon naught, but we know that vector D is vector E into epsilon naught is density of electric field lines So, from the divergence of a current density at any point in electric field is given by del dot D is equal to rho by epsilon naught. We just rearrange this equation in order to get rho. So, rho is equal to del dot E dot epsilon naught, but we know that D is equal to E into epsilon naught, that is the density of electric field lines. So, we can write rho is equal to del dot D, we will call this as equation 5. So, we got the charge density as rho is equal to del dot D. Now, from the equation of continuity, del dot J is equal to minus dou rho by dou T. Substituting phi in the above equation, so it is del dot J is equal to minus dou by dou T of del dot D, or we can write this equation as del dot J is equal to minus del dot dou D by dou T. We will call this as equation 6. Now, we got the value of what is del dot J. Now, we have in the equation del dot J is equal to minus del dot JD. Now, substituting 6 in equation 4, so del dot J is minus del dot dou D by dou T is equal to minus del dot JD. So, the operator and the negative symbol gets cancelled on both hand sides of the equation. So, we are left with JD is equal to dou D by dou T, we call this as equation 7, is the displacement current density. Del cross H is equal to J plus dou D by dou T, we will call this as equation 8. So, equation 8 is the Ampere's Maxwell's equation, where JD or dou D by dou T is the displacement current density. So, this is how we derive the expression for the Ampere's Maxwell's equation, starting from the Ampere's law in the differential form. The next expression we are going to derive is the expression for the displacement current. We will derive in this next derivation what will be the value for, or what will be the expression for JD or dou D by dou T. Expression for displacement current. Let us consider a parallel plate capacitor which is connected to an AC source. Let A be the area of the capacitor plates and D is the distance between those two capacitor plates. Let us consider V is the potential difference applied between the capacitor plates. So, consider a parallel plate capacitor connected to an AC source. Let A be the area each capacitor plates and D be the distance between the plates. The potential V across the plate is given by. So let us consider a V with a potential which has been applied across the capacitor plates. Then a V is equal to V naught exponential of I omega t, we will call this as. Then the electric field is given by is equal to V by d, that is V naught exponential of I omega t divided by d, we will call this as equation 2. But d is equal to epsilon naught E. Therefore, we can write the d as the d is equal to, we will substitute the value of E here. So, epsilon naught V naught exponential I omega t divided by d, we will call this as equation 3. Now, using d, we have to find out the expression for the displacement current density. The displacement current is given by JD is equal to dou d by dou t. This is the expression for the displacement current. Calls as equation 4. Now, substituting 3 equation 4, so you can write JD is equal to dou by dou t of epsilon naught V naught exponential of I omega t divided by d. So, this is what we have got by substituting the expression 3 in equation 4 or expression 4. So, we have got JD is equal to dou by dou t of epsilon naught V naught exponential of I omega t divided by d. Now, what we have to do is we have to partially differentiate epsilon naught V naught exponential of I omega t divided by d in order to get the expression for the displacement current. So, we can write JD is equal to, now if I partially differentiate this, I will get epsilon naught V naught I omega exponential of I omega t divided by d, call this as equation 5. But we know that the current density can also be expressed in terms of the current, but JD is equal to ID by A, or ID is equal to A into JD. We will substitute the expression 5 in expression 6. Substituting 5 in 6, hence ID is equal to A epsilon naught V naught I omega exponential of I omega t divided by d. But we know that the capacitance of the two parallel plates capacitor is given by C is equal to epsilon naught A by d. So, the displacement current becomes C V naught I omega exponential I omega t. Equation 7 is the expression for the displacement current. Now, where the displacement current is the collection in the Maxwell's equation that appears in the time varying conditions. It does not describe any movement of charges through it and its associated magnetic field. Derivation of wave equation of electromagnetic waves by using the Maxwell's equations in the free space. Maxwell's equation in conducting medium, del dot E is equal to rho by epsilon naught, or del dot D is equal to rho. Second one, del dot B is equal to 0. Third one is del cross E is minus dou V by dou T, and fourth one is del cross H is equal to J plus epsilon into dou E by, or del cross B is equal to mu into J plus epsilon into dou E by dou T. So, these are the four Maxwell's equations by Gauss law of magnetostatics. Del dot B is equal to 0, then del cross E is equal to minus dou V by dou T, and del cross H is equal to J plus epsilon into dou E by dou T, or del cross B is equal to mu into J plus epsilon into dou E by dou T. These are the Maxwell's equation in a conducting medium. Now, in the free space, the charge density and current density both are equal to 0. So, in free space, rho is equal to 0 and J is equal to 0. So, we can write the Maxwell's equation in the free space as del dot E is equal to 0, del dot B is equal to 0, del cross E minus dou V by dou T, and fourth one del cross H is equal to epsilon naught dou E by dou T. Now, these are the four Maxwell's equations in the free space. Now, using this Maxwell's equation, we will call this as 1, 2, 3 and equation 4. Now, using this four Maxwell's equation, we have to derive an expression for the wave equation for an electromagnetic wave. Now, let us consider equation 3. Considering equation 3, del cross E is equal to minus dou V by dou T. Now, we will apply curl on both sides of the equation. Applying curl on both sides, so it is del cross E is equal to del cross minus dou V by dou T. So, we have applied the curl on both sides of the equation 3. So, it becomes del cross E is equal to minus dou by dou T of del cross B. B is equal to mu naught into H. So, we can write del cross E is equal to minus dou by dou T of mu naught H, or del cross E is equal to minus mu naught dou by dou T of H, del cross mu naught H. So, this also becomes del cross H. We will call this as equation 5. Now here we have got the del cross H, but according to equation 4 we have a del cross H as epsilon naught dou E by dou T. So it becomes del cross E is equal to minus mu naught epsilon naught, also will take it outside, dou by dou T of dou E by dou T. For vector analysis, del cross E becomes del dot E minus del square E. Now, this is according to the vector analysis, which says that del cross E is equal to del dot E minus del square E. So, we will substitute this in the above equation. So, this becomes del dot E minus del square E is equal to minus mu naught epsilon naught dou square E by dou T square. We will call this as equation. So, since del dot E is equal to 0, we get minus del square E is equal to minus mu naught epsilon naught dou square E by dou T square. So, minus let's cancel on both sides. So, we have got del square E is equal to mu naught epsilon naught dou square E by dou T square. So, equation 7 is one of the wave equation of electromagnetic waves using the Maxwell's equation. Similarly, for magnetic field, del square H is equal to mu naught epsilon naught dou square H by dou T square. So, equations 7 and 8 are the wave equation for the electromagnetic waves, which we have derived by using the Maxwell's equation, where equation 7 is the electric field equation and equation 8 is the magnetic field equation. So, this is how we can derive the wave equations for the electromagnetic waves using Maxwell's equations, right. So far in this sessions we have discussed 3 derivations. One is the expression for the Maxwell's Ampere equation, second one expression for the displacement current, and third one is expression for the wave equation of electromagnetic waves using the Maxwell's equation. Thank you.